Good morning. Good morning, everybody. We are back. This is day 2 of the hackathon. Yesterday was a good start. I have to admit, the projects are interesting. People are nice. They're hardworking. And we had a good introduction and we got acquainted with each other. So today is the day where we can offer people in the audience and the competitors insight about the role of randomness in cryptography and other complementary arguments. And I'm really pleased to welcome Marco Macchetti from Nagra-Kudelski, who is going to have the honor of the stage for the first keynote speech of the day. So Marco, good morning, welcome.
Good morning, thanks a lot, Massimo.
And the floor is yours.
Thanks a lot. I will share the presentation. Okay, so I hope everybody can see the screen. So my name is Marco Macchetti. I've been working for 15 years for Nagra-Kudelski Group. Let me briefly introduce myself. I have a degree in electrical engineering from Politecnico di Milano, and I have also a PhD in computer engineering from the same institute. I've been working a lot on hardware security and also on randomness related topics. So this is why it is really a pleasure for me today to give you this talk. Let me spend just oops. There's something wrong. Okay, let me just spend a few words on the company where I work for. This is a company based in Switzerland, and our core business is in fact digital security, and more specifically we work for pay TV operators. So our main mission is to secure the content, the digital TV content. So we work with a lot of operators worldwide, and we design the encryption systems which are needed to encrypt and decrypt the content, and we also design smart cards and secure tokens for decrypting securely the content. And this is our worldwide presence. So today I will give you this presentation, and I realized that putting together a presentation on the role of randomness in cryptography, one should also speak about randomness and what is randomness and how do we measure it, and also what are the cryptographic algorithms, the different types, and how they work. But I soon realized that going deep into either of these topics would probably take an entire lecture series, and this is definitely too much for a coffee talk. So here today, I really want to speak about the connection between cryptography and randomness. And as you will see, there is a strong connection, and the concept of digital privacy and security are really founded and very related with that of generating good randomness. So I will try with a beginning which is a bit non-orthodox. This is a quite intuitive definition. When you are looking at some data, if you see it looks random, well, you can say it must be encrypted. And this seems a naive statement, but it really gets straight to the point. So it really catches a good point. It's so true that when hackers are looking for secrets, they typically look at randomly looking strings inside an executable or a computer program. And as I will tell you, the definition, the theoretical definitions in cryptography and the proofs that we have are essentially based on the concept of randomness. So starting from this seemingly naive statement, we can present some very advanced concepts. So let's try and take a look of about how randomness is used in modeling cryptographic functions. So the cryptographers came up with this idea. It's a very idealized concept, but it's useful to go through it. The concept is called random oracle. So what is a random oracle? It's a black box definition, so we don't care here about how this oracle is implemented. We just are interested in the behavior of the thing. And a random oracle is essentially an oracle, so it answers to queries, and it answers with randomly values, randomly sampled values, perfectly random values. So when an oracle receives a certain query, let's say x1, it answers with a value O x1, and the same for following queries. And these answers are perfectly random, so it's an idealized concept. But the oracle has memory, so whenever it receives a query that it has already received in the past, it answers with the same value. So it has a perfectly random generator, but it has also memory. So it means somewhere it must maintain like a big table of answers to queries. And why is this is important in cryptography? Because it can be seen as an ideal toy for cryptographers. So what cryptographers can do is to base on this idea and build proof about the security of cryptographic protocols. So the many protocols today can be proven secure if they use a function f, which is a random oracle. So this may seem a bit far from reality at the beginning, but indeed, the main goal of doing this is that any flow in the protocol must not come from the protocol itself, but from the function f, which is idealized as a random oracle. So it's really something that is useful in cryptography to prove the soundness of protocols. And we can think about building like a house, which is the security scheme, the cryptographic scheme, on the strong basis foundation, which is the random oracle. Now, this is a good tool, a good idea in theory. It's good for cryptographic theory, but it's not even, it's very far from being realizable in practice, right? Because first thing, each output must be picked truly randomly, and it must be repeatable. So the same query gets the same answer. So there is clearly a need of an incredibly big memory or circuit to implement this kind of function. So this is not a realistic function. It's a good idea, but cannot be put into practice. So cryptographers started looking for some more realistic alternatives. So still an idealized concept, but which can be nearer to reality. And this is what we call a pseudo-random function, or PRF as an acronym. This is a much more useful thing. It is a function which can be computable efficiently, but looks like a truly random function. So here we don't assume it's really a truly random function, but it must behave and it must be indistinguishable from a truly random function. So we give up the perfection, but we keep the idea. And the key here is really that a PRF is indistinguishable from a function which is picked at random from a given function set, but can be computed easily. And since it can be computed easily, now we can implement it with some computer program, or we can design a circuit which realizes this function. So the main idea here to implement PRF is coming, well, the first papers about this are coming from Shannon, and there's really a long history in cryptography in building PRFs. So the idea is to have a complicated function, right? A complex function which is not easy to analyze. And so what cryptographers do usually is to take small and simple functions and to iterate them a certain number of times. So if you look, for example, at this network here, there are a given number of bits that enter the function on the left, and there's a given answer which is given on the right. And if you take a simple function and you iterate a sufficient number of times, Well, you will have that any irregularity in the input is basically removed by the function, and by looking at the output, you really realize that you are looking to white noise. Of course, the function is deterministic, and it's easy to compute. So this output here is not really noise, but it looks like noise. And these kind of functions have also other interesting properties. So whenever you make a small change in the input of the function, this change propagates in a very complicated way through the function. And so finally, in the end, you will have an effect which is called an avalanche effect, that it's very, very difficult to be put in relation with the difference in the input. So if you use this kind of function to encrypt a lot of data, any irregularity in your data will not pop up in the output of the function. This is why it's very useful. So let's try to give a concrete, some concrete examples of these PRFs, pseudo-random functions. Well, for example, there are some functions in cryptography which are called hash functions. You may be familiar or already have heard about this kind of primitive. So essentially, an hash function is a function that can digest a message and produce a compact fingerprint of the message. So this is very useful, for example, in digital signing and also in integrity checking. So you can, here in this picture, you can see there's an arbitrarily long message. In this case, it's a picture. It gets eaten by the cryptographic hash function, and a digest is produced at the end. And since this is a PRF, there's no way by looking at the fingerprint of the message to get information on the message itself, right? But you can be sure that any message that you can input to this function will have a different fingerprint. Of course, the size of the fingerprint must be big enough so that this is true in practice. And these kind of functions are very useful. And as I already said, for example, SHA-256 is a very, very popular, very commonly used hash function, and it realizes this concept of PRF. It's a USA standard. It is fast, so given a PC today, you can hash at gigabit per second speed, so no problem. And it is the basis of a huge number of crypto systems. And to give you an idea of the importance of these kind of functions, you can think about the market cap of Bitcoin today. There are over $200 billion which are stored in crypto wallets. And these wallets and the whole system of Bitcoin is secure as long as the SHA-256 behaves randomly enough. So it's really the random looking behavior of this function is what allows Bitcoin to be a system so widely used. SHA-256 indeed is the basis of Bitcoin mining. So here I don't have time to discuss all the details, which are very interesting, but indeed you can there are some crypto puzzles that are built over this using this hash function, and by solving this puzzle you can really generate money with Bitcoin. This is very consuming. It's very energy consuming, and today there are terawatts hour of energy which are spent essentially hashing with SHA-256, so essentially producing pseudo-random values. And you can see here that the energy consumption of yearly energy consumption of Bitcoin is comparable to that of small countries. So here we are really speaking about a very big effort. Another example of a PRF is a block cipher. It's a slightly different thing, but it's quite related. A block cipher takes a small plain text, what we call plain text. So you can think about a small message, a key, which is usually secret, and produces a ciphertext, which is the encryption of the plain text under the given key. So it's very simple. Then you have more complicated constructions, but this is the basic concept. So it's another kind of PRF, and as an example, we can mention AES. AES is a very popular block cipher today. It's the most widely used worldwide. It has 128-bit keys, and it can encrypt 128-bit plain text to 128-bit ciphertext. It's another US standard, so it's I think the USA is a very strong country in the realm of cryptography. So many international standards come from the US. And today it is used to
Marco,
enable...
sorry to interrupt you, but in such a case, the main difference between the SHA-256 or whatever is that you have no size reduction. So if you input a
Correct.
text, so is that correct? Okay. Yes.
Yes, this is because the typical use of an hash function is just to extract a fingerprint
Yes,
of a long message.
Why here
you want to recover the message, right?
Okay.
So you have to have a bit bijection, essentially. Yes. So today, this block cipher is used to secure almost all communications on Earth and all secure storage. So Wi-Fi, TLS, disk encryption, all use the AES function. So just to give you an idea of how pervasive are these concepts. And for PRFs, really the key word is indistinguishability. So it's a long word, but it means that these kind of functions must be indistinguishable from random functions. And even the slightest bias, if you can find even the slightest bias in the behavior of this function, it can be catastrophic for security. So for example, a bias can help you find passwords just by looking at their hash, or can help finding a key faster than brute force, or can even allow you to steal money from crypto wallets and compromise, of course, all secure communications. So from algorithm perspective, we have today methods to conceive these kind of functions which are looking perfectly random. And usually what these functions do in reality is to act as randomness amplifiers. So they take a small secret K, which is usually the key, and can be used to produce a long stream of random bits. So this small secret, usually 128 bits. Why 128 bits? Because it's something which requires an incredible amount of time to be guessed. So this is basically what determines the size of the key of a key today. This is usually a small secret that is a key or a secret seed. It must be kept secret and handled properly. And this is why usually to protect these kind of secrets, we use smart cards or hardware wallets or any kind of secure tokens, because if we want to have secure communications and secure storage, we really have to keep these small secrets. And the easiest way is to put them in a safe, which in reality is not a safe, but just a smart card or an hardware token. And then once the key is safely stored into our safe, it can be used to produce a long stream of bits which are looking random. And it can be counterintuitive, but this is the basis of all secure systems today. So the recipe is really to take a good function that we have seen, it's behaving randomly, seed it with a small unpredictable secret and keep it safe, and then use the output to perform any crypto operation you like. But we still are confronted with the problem. How do we generate the key or seed itself? Well, you guess what? You need a random bit generator to do that. So a good key must be unpredictable, and everyone every day is confronted with this kind of problem when we have to choose passwords which must be unpredictable, right? If we choose a password with small entropy, we know that it is not safe. So for crypto systems to work properly, these keys must be randomly generated and perfectly random generated, so with a uniform distribution. So this means having a perfect true random number generator. And this can be very hard to have in practice. So eventually, there is only one way to do this, is to collect entropy from the physical world and digitize this entropy to get a stream of random bits. So this is why many secure tokens have physical TRNGs inside. And they can use different type of entropy sources, even combine different sources to obtain good keys. So if you want, you can also try generating a key with coin tossing. Why not? It's if you don't trust anyone, it can be a simple and effective way to generate a key. But usually in electronic communications, we cannot afford this kind of physical generations. So we use electronic circuits. For example, we sample oscillators or electronic noise coming from resistors or junctions. And there are different kind of noise that we can sample. Even collecting keystrokes or mouse movements can be a nice idea. And in fact, every Linux system does this kind of thing. It collects entropy in a file by looking at keystrokes and mouse movements. There is also environmental noise that can be used, audio, radio waves, or radioactivity, and photon detectors. So eventually this brings us near to the fact that a good TRNG must in some way look at quantum level behavior and effects. It's not always the case, but probably the strongest true random number generators are built in this way. But we know every physical phenomenon is imperfect, so we are not generating perfect bits, right, in this way. For example, the stream of bits can be biased, so the probability of having a 0 can be different than the probability of having a 1. And this is what you see here in the first bit string here. The chance of having a 0 is larger than the chance of having a 1. Bits can be correlated. For example, the chance of having a 1 is much higher if the previous bit is 0. So for example, if you see in this bit string, the successive bits are highly correlated. Or they can also have other non-uniform properties. For example, the bits may come in blocks of zeros, as in this third case. And this really depends on the kind of physical phenomenon that we are sampling, right? We cannot assume the perfection of the physical phenomenon itself in terms of randomness. We have a way to estimate how much entropy a given physical phenomenon produce, and this can be done simply by using the Shannon formula, and we can express the entropy in terms of Shannons per bit. So a perfect generator will have 1 Shannon per bit entropy. What does this mean finally is that each bit which is output from a perfect random number generator is a perfectly uniformly distributed bit. And if bits are non-perfect, like in this case, you will have maybe a half bit per bit of entropy or even less. But how do we achieve perfection? Because here we are interested in generating perfectly random keys, right? So again, we use cryptographic functions. For example, we talked before about the random behavior of the SHA-256, and we can in fact use this kind of function to whiten, to be able to generate the perfect keys from imperfect random bit generators. So the main idea here is that we can collect entropy like drops of water in a bucket, and every bit of entropy which comes will be collected in this bucket. And finally, this is another picture. When your pool is full of entropy, then you can output it, and it will be a perfectly random key. So in this case, our PRF acts really as an accumulator of entropy. And
Marco, can I make a small commercial?
Yes, sure.
Actually, I'm sorry, because I was telling the people in the hackathon about what we are doing with random power. And actually something that honestly surprised us a lot was the fact that I analyzing the irregularities, as you see, so correlations or unbalance in the bits or whatever, in the raw data stream that we generate, we couldn't actually, we were unable to identify any irregularity over, say, the largest set that I analyzed was 30 gigabit. So over 30 gigabit, I couldn't do it. Okay, I used the NIST, I used my own build function, I used the bool test. And so it looks like that apart from the principle is usually perfect, but the actual implementation is a lot less robust. But for whatever reasons, we apparently did it reasonably well. And so over 30 gigabit, say the Shannon entropy, Shannon's per bit that we obtained was essentially 1. That was giving us some confidence. Then the word is not perfect. And as you told me once, you always want anyway to post-process the data. But one of the advantages that we see is that since we don't have to have it, we have, say, a larger efficiency. Sorry, but I couldn't resist in telling that.
This is quite impressive. And usually we suggest in any case to use cryptographic whitening. But why? Because in fact, there can be irregularities which are very, very hard to detect. You mentioned before there is some well-known test benches to test the amount of entropy in a bit sequence. They have a battery of tests. So each test is looking at a specific regularity. So for example, a test can detect easily one kind of regularity, but not another one. And if you have a sufficient number of tests, each testing a different kind of regularity, you can be quite sure that in the end, if all say your bit string is okay, that it's okay. But really, you have no 100% proof.
I agree.
So if you have some characteristic in your physical phenomenon, it can be it can enforce a certain property in the bits which can be hard to detect. And this is why usually it is always suggested, and the norms always suggest to use cryptographic whitening because they remove any kind of regularity.
Yeah, I agree.
So here we can really see the connection between randomness and cryptography, because random looking functions and random generators finally are the basic elements of cryptography. And cryptographic functions are essential to produce good randomness. So usually in schemes, sometimes we ask for additional properties that go beyond the uniform distribution. For example, we have in RSA system, we have to produce prime numbers. In ECC, we have to generate integers uniformly distributed in a given range. So I skip the details, honestly, because we don't need to go in deep into this kind of concept. But the essential thing is that we always have to ensure the absence of bias. So today there are certifications which can be used to certify that a given system is behaving correctly in terms of randomness. For example, there's a FIPS validation coming from the US. There's a common criteria which is mainly done in Europe. And they have different security levels. So if you have a certified product, it's really for a customer, it's really an insurance that your product is well designed and behaving correctly. But even for certified products, sometimes things can go bad. Because why? Because cryptography is really tricky. For example, there was a vulnerability discovered in Infineon smart cards in 2017, and which affected a lot of products worldwide. And this was not done, was not due to the particular structure of, it was not due to the weakness of the random generator, which was very good, but to the particular structure of the randomly generated primes. So even if you have a perfect random number generator, you have to be careful in how you manipulate the random bits. And researchers proved that just by looking at this kind of keys, you can easily crack them. Well, easily, what does it mean easily? For small keys, it's a matter of hours on a CPU. For longer keys, for example, today we commonly use 2000 bit RSA keys. And it may seem, if you see here, the effort of cracking these keys is 140 years in terms of CPU time. So this may lead to say us to say that it's not crackable in practice, but this is far from reality, because today, for example, you have Amazon, which provide you a service, so you can rent any amount of CPU time on their systems. So by putting sufficient money into this, you can crack these kind of keys in a matter of a day using Amazon. Of course, you have to be ready to spend $20,000 to do that, but maybe the importance of the key that you want to attack is worthwhile. So this is a very considerable weakness. Another example is digital signatures. They also use random numbers because they need it to produce a signature. This can be used, for example, in a gaming console. When you load a game, a program, the console will authentify the program to see that it's really genuine software. So it's coming from a trusted manufacturer. And how is it done? By looking at digital signature. So there was an epic failure from Sony, the PlayStation 3. The hackers were looking at how the games were signed, and they discovered that a nonce, so a random number that was used to generate the signature, which should have been different for each signature. Well, it happened that someone used twice the same random number to sign two different programs. And this was a catastrophe because it allowed the hackers to retrieve the private key that was used to sign. So the Sony key was compromised, and then it opened the bar to loading custom software into the console, and basically to the pirating of games and sharing of games. So we can see how really a small error can lead, related to random numbers, can lead to catastrophic results. Well, this was just one last thing I would like to mention, is that randomness is not only important in theory, in cryptography, but also in practice. In fact, implementations of cryptographic algorithms can leak secrets because of many things. For example, the current absorption of the circuit, the electromagnetic emissions, the execution time are all things that can be monitored by hackers. And by looking at specific characteristic, they can try to retrieve the secret which is manipulated by the crypto system. This kind of attack is called side channel attack. And these are very powerful. And well, it happens that randomness can also help us avoid these kind of attacks. So there are many techniques known today, like data masking and threshold cryptography, which can be used to make the current absorption of or the electromagnetic emission of a circuit random looking. So an attacker has no advantage in looking at the emissions of a circuit to retrieve the key. And this is, again, one very important use of randomness. So I hope I gave you a nice idea of how cryptography and randomness are really related. So randomness is relevant because it allows to define good functions for cryptography, to prove security of protocols, to generate keys, to secure digital signatures, and protecting algorithms against side channels. So it's a fundamental element of cryptography. And cryptography also helps in generating good randomness. As we have seen, cryptographic functions are used to generate unbiased bits as entropy accumulators and to construct cryptographically strong TRNGs. So here, I hope I gave you an idea of how the two things are really related.
Thank you very much.
Thanks a lot.
Thank you very much, Marco. Very, very intriguing and very interesting. Do we have any question or curiosity by the audience?
Well, I might have some question, maybe very naive, but
Please.
so, well, first of all, thank you for your speech. I have a couple of questions actually. So you mentioned all those approaches for true random generation. The one I knew from years ago when I was a student was also the approach of camera looking at the weather and generating random according to that. So you mentioned the Shannon formula, and now Massimo, you also mentioned your approach. How do all these true random approaches compares in terms of Shannon formula? Like how close are we to perfection somehow?
Well, first we have to say that Shannon formula is simple, but it has some limitations. So it doesn't work well if you have a correlation of bits, for example. So I think the question is how to compare the physical phenomenon that can be used to produce random numbers in terms of the quality of entropy.
Yes.
And I think the simplest idea that we can have, like looking at the environmental noise or this, let's say, high-level structure of the physical world, is sometimes a bad idea because they can be very influenced by, for example, if you look at the radio noise, you can get some radio. Just a silly example, maybe, but you can get some radio station, and you can have something which is not really random. So you have really to extract noise. So usually you want to look at background noise. And I think the most intriguing and the most interesting as a future proof system is one which really is able to amplify the quantum noise. So the noise, the unpredictability which is naturally there at quantum level.
I agree. Because whatever else you do is in principle perfect, but then in the actual implementation, it can be easily biased. And even when you go quantum, you have to be very careful. For instance, Marco was mentioning one of the fundamental quantum true random number generator, which is based on single photon detection. This is relatively easy to explain and also easy to tell why it can be biased. Say, for instance, that you have, I don't know whether you can see actually my hand, say that you have a source which is emitting one photon at a time, which by itself is not trivial. And then say that you have a beam splitter, say that you have a detector with a certain efficiency, and the efficiency is 50%. So you have an equal chance to see or not to see the photon. So it's very, very fundamental. Now, this is perfect. If I shoot a photon and then the detector doesn't see it, I set the bit to 0. Otherwise, I set it to 1. And how can I bias it? First, there is no single photon source. So usually, the emission in the number of photons is Poissonian. So it's random itself. But if I knock at the door twice, then obviously is easier that I open the door. Then the detector can be 50% efficient, that is to say, equal chance of seeing or not to see the photon. But there is no such detector. Every detector can be close to 50%, but how many digits you go close to perfection? So you see, the principle is perfect, then the actual implementation can contain itself so many little parameters that are, by the end of the day, biasing the output that you have. So
yeah. Well, a biased generator is not bad by itself. As we have seen, you can use it very easily to, yeah. So,
but as long the highest, the most important the bias is, the less efficient is the process.
Of course, yeah. And then we didn't mention, but we have also to take into account the speed of generating random bits is a very important parameters for some system.
Yeah.
Okay. Well, thank you.
You're welcome. Do we have other questions?
I have a question. Can you hear me?
Please. Yes, we do.
Yes.
So I wanted to ask about the natural bias. So as you said, there is a chance for every kind of phenomena to have a bias just because of physics and there's other noises that can interfere into it. How do we make sure that we cannot, like, we exclude these biases? Or in the case when we use quantum computers, we also have the electrical biases and other generation problems. How do we make sure that this is not in our data?
Well, I think, like Massimo said, there are today publicly available programs or test suites that can be used to analyze a certain quantity of bits coming from any given random generator. So if these suites usually apply a battery of tests, so a high number of tests, which are each of the tests is testing for a different regularity. So whenever you have a result which says that no test was able to detect bias, then you can be almost sure that you are high confidence that your generator is behaving very, very well. Of course, you never have certainty, but in randomness, there's no such thing as certainty, right?
Absolutely. For instance, I think if I'm not mistaken, in the NIST suite that we use, you have something like 186 tests that don't run in parallel. And of course, as Marco said, they give you a probabilistic statement. So if you fail, you can make sure that you have a bias. If you do not fail, actually you have a probabilistic assessment about the quality of the string.
So some tests can also be parameterized differently. So for example, you have tests that look at single bits, but then you can look at distribution of single bytes or at single words of 32 bits. So if you know that your generators, for example, is producing single byte, 1 byte at a time, you may be more interested in looking at the distribution of bytes than correlation.
I agree. For instance, in one of the implementation of our system, every event, what we call an event, is actually providing 4 bits. And then you always get started by looking at the correlation within set of 4 bits, because this is strictly related to the phenomenon that you use. And then once this is done, you look to a longer sequence.
So sometimes, okay, you have many tests, but also some knowledge from the tester is helping detecting detecting weaknesses.
Oh yes, a blind test usually doesn't work. But I tell you something more, as one of the people that designs such a system, it's important to have knowledge, because when you fail, and usually you start by failing, honestly, then this is flowing back into the design of the system itself. Sorry, they were knocking at my door. But it's important, the higher the number of tests that you run, the better it is. But keep in mind that it will always be, say, a deterministic statement on the failure and a probabilistic statement on the success.
But what about the cases, for example, when we run a lot of tests, like you said, 100 or more tests, and only one of them comes back as a failure? Does that mean that our numbers are random enough, or do we need to do something?
Look, this is really... Okay, Marco, you go first.
Sorry. In fact, these tests have a certain failure probability, and it's important that they can answer with a failure. So usually they are trimmed in a way that the rate of false positive, so if you have a failure which is not really related to a weakness, but it's still a failure reported by the test, this must be not negligible, because otherwise your test will always say that your data is looking random. So it can happen sometimes, even for a nearly perfect generator, that some tests fail, and this is already taken into account. For example, in the NIST suite, there is a certain failure rate which is accepted. So
because again, you do it in a probabilistic way. So
correct.
It may well be that you have really a failure that occurs, and it's actually an indication that you're doing well. So never forget the Bamford law. Huh? I mean, the Bamford law is a good example, not in cryptography, where you have to be aware that something that is too perfect is probably biased. So you have to consider a certain amount of failures. Usually when I'm testing 1 to 2 gigabit per file, and there I'm running 180 or 186 tests. I know what I can expect, and I know the number of successes, number of failures, and then you consider just a binomial distribution, and you know how often you can expect to have a failure.
Then if a single test is always failing, that it may be an indication that there's some regularity in your data which was detected by this specific test. So then you have to probably look at how the test is working and which is the regularity which is detected. And
I
then
agree. This is also very important. If you have if the failing test is 1 out of 186 in a random way, randomness again, then you can be reasonably safe. If it is always the same, it's a good indication. And then also the length of the chunk that you're analyzing is important. For instance, usually in the NIST, you use 10 to the 6 to 10 to the 7 bits. And again, if you have anything that goes beyond the length of that you use, you won't be able to see it. And I have one example where we were setting up our system, honestly. We had a regularity, say an imbalance in zeros and ones that was happening over a series that had to be as long as 250 to 500 million bits. Then fluctuations for NIST was within the stochastic variations. But then you were unable to see biases that were happening on a longer time scale. So you have to get a feeling by doing, honestly, like most of the tests. Huh?
Okay, thank you.
Any other curiosity or question to Marco? Marco, you were very good. You triggered fantastic reactions.
Thanks a lot. It was a pleasure.
Okay, if we don't, then we thank Marco again. Marco, if it's not a problem for you to share the slides, we keep it in
sure
just to, to document what we're doing. And we let you know the outcome or the competition tomorrow, and we keep in touch. So thank you very much. Have a good day.
Thanks a lot. Have a great day. Bye-bye.
Thank you.
Thank you for your presentation. Bye.
Thank you. Bye-bye.
Bye-bye. Okay, so ladies and gentlemen, we thank again Marco. Keep working, keep coding, and we are back saying in 1 hour or so for the next one, which is actually by the CTO of Infer, who is actually tackling the problem on a different point of view, and it's going to be possibly as interesting as Marco. Marco is a great engineer. I mean, we got in touch with him, and discussing with him was always bringing something good. So see you in a while.